Okay, good morning. Well, good news. There's no homework coming out today. Actually, even if you look ahead carefully, there's no quiz in the upcoming Tuesday. Yeah, the downside is after spring break, you come back, and then we have a class, and then we have a midterm, which is a bit awkward, but it's somehow the only way the schedule would work out. Yeah, so your duty during spring break is to study for the midterm. We'll try to have some practice problems and things come out soon. Okay, so today's topic is some famous theorems in mathematics you may or may not have heard of, called Gödel's Incompleteness theorems. This is Kurt Gödel. And it connects actually a little bit to more topics we've seen earlier in the course so far, the topics on logic and undecidability. And you can see Kurt is looking a little bit stressed out here. And actually, normally if you see proof of these theorems, it's like very complicated and tiresome. Like when I was an undergraduate, I took a senior level class about logic, and we spent like a really long time, and like finally we proved this at the end of the course. But actually, if you take a computer science perspective, I claim that actually the proof of these theorems is quite easy. Actually, if you look very carefully at like lecture 6 that Anil gave about uncomputability and undecidability, he basically already proved one of these theorems. So once you take the computer science perspective, I think they become not so bad. And I like this a lot because I think this is like a great application of theoretical computer science back to mathematics. So I mean, the mathematicians have this very complicated theorem, but if you look at it with a computer science perspective, it's not so bad. And in fact, it's okay. It's not so easy, but if I just jumped into the proof, then we would be finished in like 40 minutes, and I don't want to do that. So let's kill some time by reviewing some older material, which will help us understand the proof a bit better. I should say, it still actually may not take us all of the class. So since it is, still a tricky logic class, you should feel free to ask, lots of questions and try to slow me down. Okay, so let's go back to lecture 3, so long ago, where we talked about the formalization of proof. So one thing we talked about way back then, I invented this ridiculous acronym, GORM, standing for good old regular mathematics, which is the mathematics we use in our daily life when we're writing the homeworks, when we're solving problems. They're written in English. They're based on, our naive concept of what is logical and what's a valid deduction. And that's great. That's how math works. That's how we prove things. But, back in this lecture, I also told you some stories about people that thought they'd prove some things, and it turned out to be incorrect, and how it made mathematicians in the olden days nervous a little bit. And so they decided, well, this GORM is all well and good, but we'd also like to maybe invent like a mechanical logic for talking about proof so that we could really be sure whether or not we've proved something in a very careful and formal way. So in the early 20th century, late 19th century, they started to try to develop like a very mechanical, purely formal reasoning about proofs. And it involved 2 tools that we talked about, first-order logic and also deductive systems. So I'll remind you about these things. So first-order logic was all this stuff with, like the for all and exists and implies and the functions and the constants and the relations. These function names and constant names and relation names were called the vocabulary. And one basic concept we had when talking about first-order logic was tautologies. So these are sentences that are true for every possible interpretation. So no matter what the constants and the relations and the functions stand for, the sentence is always true, which kind of means that it's true only for like logical reasons only. Okay, so an example is this sentence here. For all x, if x equals a, if for all x, x equals a, then next of a equals a. Okay, and here it doesn't really matter what in your interpretation next means or what a means. It's got to be true. If everything is equal to a, then whatever next of a is, it also equals a. Okay, or in this one, if this constant c satisfies this is cool relation, then that implies that there exists an x such that is cool of x. This is true no matter what is cool and c mean. Okay, so this was the concept of a tautology, something that was always true regardless of the interpretation. Okay, and we had a theorem by Gödel already with the substring completeness in it, called Gödel's Completeness Theorem. And that was a very cool theorem and a somewhat difficult theorem, saying that there's a purely mechanical way you can check whether or not a sentence is a tautology. If you remember in propositional complexity where there's no for all and there's no functions or anything, it's just and or not, implies in propositional variables, it was quite easy conceptually to test whether a sentence is a tautology. You just had to list out the truth table. I mean, try all possible truth assignments and see if it always made the thing true. But here it's not so clear. Maybe these ones we kind of reason naively why they're tautologies, but to really prove something is a tautology, it seems like you have to try all possible interpretations to see if it makes the sentence true. But Gödel proved this cool theorem, this completeness theorem, which says that there's some kind of deductive system that can generate all the tautologies. So there's some kind of mechanical, just a simple deductive system with initial objects and deduction rules such that you could generate all tautologies. And that's usually called the deductive calculus for first order logic. And we don't want to actually say what it is because it takes like a couple of pages of paper to write it all out. But the summary is, it's one of these deductive systems, and it's actually a deductive system where there's sort of a lot of initial objects, but only one deduction rule. Okay, so there are a bunch of initial objects, or axioms, and these are all statements which are obviously tautologies, kind of like the ones on the previous slide. And there's one deduction rule, which is that if A is a tautology, or if you deduced A, and you've deduced A implies B, then you're also allowed to deduce B. And that's a sensible rule. I mean, if A is always true for all interpretations, and A implies B is always true for all interpretations, then B is also true for all interpretations. So good. So it's easy to show that in this deductive calculus, which I didn't write down, but I could have if I wanted, everything that's deducible is a tautology. And that's kind of like by design. You just set it up so that these are all obviously tautologies, and the deduction rule sort of preserves tautologies. And the tough thing that Gödel showed is that every tautology is deducible. So actually, you can get every tautology just by mechanically applying these deduction rules. One slightly annoying thing that I have to point out, it's important to say, though, is that it's actually not even just a finite list of initial objects, because then you could kind of tell you would only sort of be able to get not too many tautologies. It's actually a family of initial objects or a family of axioms. Actually, we'll see an example of that later. For example, here, like an initial object or initial tautology are things like this. If A is any sentence at all, then A or not A is an axiom, or it's an initial tautology. Okay, so that's actually infinitely many tautologies that you can get right there. But it's kind of OK, right? I mean, these are all, no matter what sentence A is, A or not A is always true. Okay, or here's another example. So as I said, it actually has, this deductive system actually has infinitely many initial objects, but they're all very simple. They're like this nature. Any questions so far? Actually, there's one aspect of this that we didn't mention way back in lecture 3 because we hadn't talked about computation yet, but I put it up here. It's just like a side observation that's good to remember, which is that this deductive system has like a computability property in the sense that there is an algorithm which, given a sentence, decides if it's one of these initial tautologies. So even though it has infinitely many acceptable initial tautologies, like A or not A, there's still an algorithm that looks at a string and decides if it's one of these tautologies. For example, it's not hard to write an algorithm that looks at a string and decides if it's of this form, A or not A. Okay, it just means that these initial objects, although there are infinitely many of them, they're not completely arbitrary. They have a nice simple system, and it's computable in the sense that there's an algorithm that will tell you if you've written one down validly or not. Does that make sense? Okay, so let me give you sort of the upshot of this completeness theorem. It's that there is some Turing machine algorithm which, given a tautological sentence S, finds a deduction of it in this first-order logic deductive calculus. So Gödel's theorem, completeness theorem, tells you if you have any sentence which is a tautology, you can deduce it using this deductive calculus that the logicians invented in the 19th century. So let me ask you this. Why is there an algorithm that can necessarily find this deduction? So Gödel told us, this Gödel completeness theorem tells us that if a sentence is a tautology, there is a deduction in this deductive system that deduces it. Now I'm also telling you that in fact there's an algorithm which would take this input sentence S and finds this deduction. Yes?
Because you can generate all tautologies up to the length of the tautology you're looking for.
Yeah, you can just do a brute force search. So if I give you a sentence and it happens to be a tautology, you can find a deduction for it like this. I mean, just try all strings of length 1, all strings of length 2, all strings of length 3, and then check that string to see if it encodes a valid deduction of S. It's a very slow algorithm, but it's an algorithm. I should emphasize that in this class, we're going to be talking about, this particular lecture, we're going to be talking about algorithms and computability and so forth. And we're not going to be worried about complexity at all. So all the algorithms we talk about might be very slow. They might be crazy brute force algorithms. But we only care about computability versus non-computability. This actually might remind you, I mean, as a little side note, back on for midterm 1 practice problems, there was some number 11 about tweeting Turing machines. I don't know if you remember that. But the problem was to show that the language of all sentences which are tautologies in first-order logic, given a fixed vocabulary, is tweetable, which basically meant that there was a Turing machine that could print them all out. And actually, that problem was a little bit harder than this observation. I mean, it used the idea that if you want to check if a sentence is a tautology, you can just try all strings to see if they're valid deductions of it. Okay, any questions? You guys remember all this stuff very well, or you're still waking up to it? Now we'll see. If you have any questions, let me know. Okay, so I mean, the mathematicians invented all of this stuff, not because they were particularly interested in tautologies per se. I mean, just checking whether a string is a tautology is medium interesting. But the reason they cared was because this connection between tautologies and entailment. So the reason they cared was this. Maybe they did a lot of proofs about I don't know, numbers, multiplication, prime numbers, factorization, basic arithmetic theorems. But then they wanted to say, well, just to be really sure, maybe I proved Fermat's last theorem, but I want to be really sure that I didn't make any mistakes. So maybe I could totally formalize the proof. Okay, and how does this sort of proof formalization project go? You think of some universe that you want to reason about. So perhaps if it's Fermat's last theorem, it would just be the natural numbers with multiplication and addition. And you invent some appropriate vocabulary that talks about the objects that you care about, maybe you have some function names for plus and times. And then you start by just writing down some sentences which are not necessarily always true, but you're just sort of positing that they are true in your interpretation you have in mind. So you might write down some axioms that say things like addition is associative, and addition is commutative, and multiplication distributes over addition. So you write down some sentences that are true for the interpretation you have in mind. And then you kind of see what these sentences or axioms entail. Remember, entailment means to say that some axioms entail a statement T is to say that assuming the interpretation makes the axioms true, it also makes T true. Or we also saw there's a way you could phrase it in terms of tautologies. It's to say that the axioms entail a sentence T if A1 and A2 and ... AM implies T is a tautology. It's really saying the same thing. Whenever you have an interpretation that makes all the axioms true, T should also be true. And this is really encoding like what it means to say that the statement T like really is valid and follows logically from the axioms. So if the axioms are some basic axioms about arithmetic and T is Fermat's last theorem or some other simpler theorem maybe, then to check whether or not your theorem really follows validly from the axioms is the same as checking whether this thing is a tautology. And now this Gödel completeness theorem tells us, we understand things about checking whether something is a tautology. It's equivalent to whether or not you can deduce this sentence using this deductive system, deductive calculus. Okay, so once you write down your axioms and you're curious about whether or not you can use these axioms to prove a statement T, it's really, the nice thing about Gödel's theorem is you've really made it into a completely mechanical problem. You just have to check whether this deductive system, which is some system for manipulating strings, can spit out this tautology. Let me give you some example. So, in the late 19th century, there's an Italian gentleman, Peano, who tried to sort of set up this formalization process for reasoning about proofs involving natural numbers. Every natural number is the sum of 4 squares, or every number has a unique decomposition into prime factors. Theorems like that. So he invented a pretty simple vocabulary for talking about the natural numbers. There's a constant named 0 that was supposed to represent 0, and a function successor that's supposed to represent x plus 1 and plus and times. And he wrote down these 7 axioms. Actually, the first 6 are just axioms, and the 7th one is a family of axioms. That says nothing comes before 0, and successor is injective, and x plus 0 is x. Some very basic statements. And induction basically is mathematical induction. And then they tried to reason about whether you could formally, purely mechanically deduce all these theorems about arithmetic just using these axioms. And they empirically found that it was very successful. They could pretty much convert any good old regular mathematics proof about natural numbers, if they wanted, into like a totally formal proof involving starting from these axioms and using deductive calculus to generate new true statements. So then they also got very ambitious, and they were like, that was just about, natural numbers. Like, we couldn't encode theorems about calculus using it, for example. So they were like, let's try to do this for all of mathematics. So they needed a language, like a mathematical language, to talk about all of mathematics. And they decided on set theory, which was probably not the best choice, but it worked. And because they noticed, if once you've defined sets, you can invent definitions for things like ordered pairs and ordered triples. You can define functions in terms of sets. You can define the natural numbers in terms of sets, integers, graphs, rationals, Turing machines. A Turing machine really is just, remember, it's like a 7-tuple with like an alphabet set and a tape alphabet set and a transition function. So they noticed that you can define pretty much everything you want using sets. And then they're like, okay, let's make up some axioms for set theory, and then maybe we can have like a rigorous system for thinking about proofs of any statement in mathematics. And that worked pretty great too. It was successful. So this guy Zermelo and a few other people invented a pretty simple set of axioms for set theory called ZFC. So today I'm going to constantly say this triple of letters, ZFC, ZFC. It means basically the axioms of set theory, but basically it just means somehow the basic rules of mathematics. So I had 9 axioms saying things like, if 2 sets have the same elements, then they're equal. And if you have two sets x and y, then there's a set z whose two elements are x and y. Okay, and some other like basic things that are true about the world of sets. And then they said, okay, like can we use these axioms to start proving true things about functions and tuples and numbers and rational numbers and real numbers and so forth. And they found out that they could. I mean, it worked. So, by the end of like the 1910s, 1920s, they kind of decided that this could work. Like you could really formalize essentially all of good old regular mathematics. Every theorem that you proved, you could, if you wanted, formalize it as, start with these 9 axioms, ZFC, and do like a lot of steps in this deductive calculus, and you could prove any theorem that seemingly you wanted to prove. So they were mostly pretty happy about that, except that it was super painful. Like if you remember this guys Russell and Whitehead, they tried to like write some books where they actually did this. And I don't know why it took them so long, but they didn't get up to 1 + 1 = 2 until the 379th page. So they kind of convinced themselves that it could be done, but then they're like, well, let's go back to just writing good old regular mathematics. And I suppose like they were like, if really a dispute comes out, like, did you prove this correctly or not? You could maybe imagine going all the way back and like writing it down formally and checking whether it follows all the rules. At least in principle, except that back then they could not do that, but we have computers now. And now we actually can kind of do this. We're actually at a very interesting time in mathematics. We're sort of right on the cusp of being able to actually formalize mathematical theorems. So there's this concept of computer-assisted proof, which is an active area of research, especially here at CMU. And it involves building software that does two things, one simple thing and one more interesting thing. The simple thing is that it has a component that can just check, like a deduction written with like the axioms of ZFC and the deductive calculus, check whether it's like a valid deduction. And that's not very hard at all. I mean, the painful thing is you have to like actually crack open a textbook to see what the 9 axioms of ZFC are. And then also you have to crack open a logic textbook to see like the 10 rules of this deductive system. When you type it all up, eventually you can write this in like 400 lines of code. It just checks that a math theorem that's been encoded in this formal language really follows all the rules. The more interesting thing that's like some kind of combination of mathematics and HCI and other things is to help human mathematicians convert their GORM proofs into this like coded up format. So this is the trickier part, but it's been somewhat successful. And I told you about actually some famous projects for doing this for very complicated theorems. Probably these are the most famous 3 theorems that have been actually verified in this way. The 4-color theorem, some group theory theorem, this Kepler conjecture done by the guy at Pitt. So it is possible. Also, ironically, they also have done it for this Gödel incompleteness theorem that I'll talk about today. Okay, so people basically could convince that you can, I think are now pretty convinced that you can more or less, if you really want to, take any like good old regular math proof that you would write on paper in English, and you could convert it into this like formalized proof that you can check mechanically. So it's kind of the end of this recap of logic, but what I would like you to remember is, among other things, if you take like a theorem that's true, like the 4-color theorem, that says that if you have any graph which has the property that it's planar, which means so there's a way to draw it on a piece of paper so that the edges don't cross each other, then there's a way to color it with 4 colors, meaning give colors to the vertices such that no edge has the same color on both its endpoints. It's some famous math theorem about graphs. It's true. It's quite complicated, but there is a Turing machine. Once we know that it's true, we can write down a Turing machine which will eventually print out a proof of it. It'll take like a really, really, really long time, but it's just this. You just try out all strings of length 1, 2, 3, 4. For each one, check if it's a valid deduction, starting from the axioms of ZFC, applying these deductive calculus rules, and ending with the statement of the 4-color theorem. So this would be very slow, but it's an algorithm that would do it. OK, any questions? This would be like some 500 lines of code. I mean, the painful thing is just writing down all the rules of ZFC and all the rules of the deductive calculus. OK, so let me move a little bit forward. In lecture 5, we talked about Turing and the definition of computability and decidability and Turing machines. And then in lecture 6, we talked about computability and uncomputability and the halting problem. So let me remind you about those things. So we invented the notion of a Turing machine, which I guess you remember. And we had this definition of a decidable language. So a language L is decidable, or sometimes you can say computable. It's the same thing. If there's a Turing machine M, or in your head informally just think if there's an algorithm M, with two properties. The one key property is it has to be a decider Tm. It has to halt on every single input. It should never get into an infinite loop. And it's supposed to correctly decide if a string is in the language L. So it should accept all the strings that are in the language and reject all the strings that are not in the language. And that's what it means for a language to be decidable or computable. Anything that can be solved by an algorithm that never gets into an infinite loop. OK, we're very happy when a language is decidable. That's the first step in dealing with it. But unfortunately, we found that there are some undecidable problems. And not only there's some undecidable problems, which you can prove kind of easily by checking that the set of decidable language is countable, but the set of all languages is uncountable. Not only are there some undecidable problems, there's some very natural algorithmic tasks that you would really genuinely like to solve, which are unsolvable. They're uncomputable. And this was a theorem due to Turing. And his famous example of a computational task that you would like to solve, but you cannot, is the halting problem. So to remind you about that, we say halts is the language of all strings which encode pairs, a Turing machine, and an input string x, such that M halts when it's run on x. Okay, or more informally, it's the set of all pairs of pieces of code and input strings, such that this code, when run on this string, halts, does not get into an infinite loop. And his theorem is that this is undecidable. There's no algorithm that can tell whether this piece of code will halt on this input that works for all pairs of code and input. And this is a very compelling theorem, and it's very important to remember, it's a very strong statement. It's not like we don't know how to solve this problem efficiently. It's not like we don't know how to solve it. It's like we know that it cannot be solved by any algorithm. You would want to solve this problem, but you cannot. And let me tell you the proof. The proof was kind of easy. It fits onto one slide. And I'll remind you of it. So it's a proof by contradiction. We say, OK, imagine there is some Turing machine, which I'll call M sub halts, which is a decider Turing machine. And it correctly decides halts. Imagine you could solve this problem. And the proof goes the way that a lot of these things go. We're going to see more proofs like this today. It invents a new Turing machine based on M sub halts that uses M sub halts as a subroutine. And it's going to involve running the program on itself or something. And it's going to get a contradiction out of that. And therefore conclude that M halts can't exist. And therefore, halts cannot be solved by any Turing machine or any algorithm. So what is this new Turing machine? I'll call it D. So D takes one input, just the encoding of a Turing machine M. And it sort of uses this hypothetical halting checker to tell if M would halt when run on itself. That's always the good trick. You ask, would M halt when you gave it the code of M as the input? And you're assuming you have this magical halting checking program that can tell you the answer. So D gets back the answer. And it does the reverse. That's the other trick. That's sort of the diagonalization trick. You do the reverse of what the answer is. So if this call accepts, meaning that M does halt when it's run on its own code, then D goes into an infinite loop. And if the call rejects, meaning that M doesn't halt when run itself, then D halts. Let's say it accepts. So if you had this Turing machine M some halts, then this is really like a 5-line piece of code that calls this as a subroutine. And you can get a contradiction just by imagining what would happen if you ran D on itself. So how does that work? If you run D and give it its own code as its input, just this block of code, well, D uses M halts to correctly decide whether D of D halts or not. And if it does halt, then D goes into an infinite loop. And if it doesn't halt, then D halts. So sounds funny, but like that's it. That's the contradiction. So the only thing that could go wrong is that this assumption was bad, and therefore there's no algorithm that can solve the halting problem. OK, so that's the very powerful Turing theorem about how the halting problem is undecidable, uncomputable. And once you have this theorem, it's actually pretty easy to prove these Gödel incompleteness theorems that we'll talk about today. In fact, Turing already pointed this out, that you can prove the first Gödel incompleteness theorem almost immediately once you have this theorem. OK, so that is the end of the recap. So now we are back to today's lecture about these theorems. Any questions? OK, so to explain what's going on, imagine like you're sitting there and you saw the proof that halts is undecidable, but like let's say you really can't believe it. Like you're like, there's got to be a way to write some code that can check whether some other piece of code will halt on a given input. You know, maybe you just can't believe it. So, you know, what might you try to do if you had to try anyway? Like if you decide to not give up and try to write a program H, which on input M and X tried to decide if M of X eventually halts. And it's not so easy. Here's an example program that might be tricky for you. I don't want to get into this too much. I put it up a bit for fun. But imagine X is the empty string, and M is this pretty simple piece of code. I didn't write down all the pseudocode, but M like goes in a loop. It looks at 4, 6, 8, 10, 12, 14. And for each one, like 10, it goes through all the numbers between 1 and 10 and checks if they're prime and checks if 10 minus that number is also prime. So it checks if the number can be written as the sum of two prime numbers. So it's like 4, 2 plus 2. OK. 6, 3 plus 3. OK. 8, 3 plus 5. 10 is 5 plus 5. 12 is 5 plus 7. 14 is 7 plus 7. So it goes for a while. And if it ever finds an even number that like it cannot write as the sum of two primes, then it halts. How would you write a program H that could tell whether this program M halted on the empty string inputs? It's not so easy, right? It seems like you have to understand something about number theory. You have to understand whether every even number is the sum of two primes. If every even number is the sum of two primes, then this program will never halt. But if there's some even number which is not the sum of two primes, then this thing will halt. So your code has to somehow be able to figure that out. And actually, currently, nobody in the world knows if this program halts or not. So it looks like a tricky task, actually, if you think about it from this perspective. And maybe like the best thing you could try is like, I don't know, like maybe you could have H simulate M of X for like 1 billion steps. If M of X halts, then you can say, all right, it halts. But you know, then you're stuck, right? Like after 1 billion steps, you're like, well, it's still going. It's hard to tell if it's in an infinite loop or if it's eventually going to halt. So that's the trouble. But Gödel had a very interesting idea. I mean, he was smarter than that. I mean, he actually, I think, probably knew it wouldn't work. But he's like, here's a very creative way you could try to solve the halting problem. It's not just, you know, simulate it for 1 billion steps and see what happens. Like, it's a very crazy, creative way to try to solve the halting problem. But if you read his paper, it's impossible to understand. And like, I think like Turing could have explained it much better. So let me explain it as Turing might have explained Gödel's idea. Okay, so here's the idea. You're trying to write a program, h, which on input m of x decides if m of x eventually halts. Here it is. You go for k equals 1, 2, 3, and you go for all strings p of length k. So you go through all strings p. And then you check if p is a valid deduction, let's say in ZFC or whatever, for the statement m of x eventually halts. And if p is, then you're like, great, let's output, yes, m of x halts. And at the same time, while you're here with p, you also check if it's a valid deduction of the statement m of x eventually loops. And if it does, then you're like, great, let's output no, m of x loops. So you like search for a proof of the answer one way or the other. And as soon as you find such a proof, you output the associated conclusion. Now, it's a very good idea for an algorithm. Could be slow, but it might work. Well, actually, does this algorithm work? Yes, no, or maybe. Is this a correct decider for the halting problem? No, it's not. We've just proved there is no algorithm that solves the halting problem. Like every other single algorithm in the world, this algorithm does not solve the halting problem. Because I just showed you this one slide proof that no algorithm solves the halting problem. So in particular, this algorithm does not solve the halting problem. But what does it mean for an algorithm to not solve the halting problem? Either has to get an answer wrong, but that doesn't look like the case. The main way in which you would fail to solve this would fail to solve the halting problem is that it would not be a decider algorithm. It would get into an infinite loop. It would run forever. That's the reason why this would not solve the halting problem. So what does that mean? It means there must be some input to this algorithm. Remember, an input is a piece of code m and a string x, where this algorithm, fails to solve the problem, and basically that means gets into an infinite loop, which in turn means it doesn't find a proof that m of x halts, and it doesn't find a proof that m of x loops. In other words, by Turing's theorem, basically there has to be some input, a Turing machine m and a string x, such that there's no proof using the laws of ZFC and deductive calculus of the statement m of x eventually halts or m of x eventually loops. But m is just a Turing machine and x is just a string. It either halts or it loops. One of these two statements is true, but whichever one it is, there's no proof of it in ZFC and deductive calculus. And that's basically the Gödel's first incompleteness theorem. There is a true mathematical statement that cannot be proved. Well, it cannot be proved in this formal system, the axioms of ZFC plus the deductive calculus. Which at first maybe you might not be, if you knew nothing, you might not be so surprised because, I don't know, you just invented these axioms and maybe they don't do a good job of proving things, but it was, like many years of experience showing that, seemingly anything that you wanted to prove, you could prove using these axioms. But turns out there's at least one true statement which you cannot prove. Yeah, so that's basically Gödel's first incompleteness theorem. Let me put it back up there. Is there any question about this? You should have some question. I kind of cheated you a little bit at some point. Does anybody spot where I kind of cheated? I cheated somewhere in going from this slide to this slide. Yes?
Is it like, how do you write that statement?
No. If I give you a string, basically, this is something we didn't try to do in practice. I kind of just told you that's possible, but it's basically true that, any normal looking math statement, you can write it more formally using the language of ZFC and deductive calculus. So if you're staring at an explicit Turing machine with 15 states, in this transition table and a specific string x, it's like 0, 1, 1, 1, 0, 1, there's no problem in writing, the statement m running on x halts, or the statement m running on x loops, using the language and vocabulary of ZFC. I mean, it's annoying, but in principle, there's no problem in doing it. Yeah?
Does it have to do with the fact that H only checks finite length proofs?
The question was, does it have to do with the fact that H only checks finite length proofs? No, because this is maybe a philosophical thing, but by definition, proofs are only of finite length. I mean, a proof is, by definition, a finite length object. So in math, we only admit proofs that are finite length. Yeah?
It could be that instead of never finding a proof, the algorithm finds a proof that proves the statement that's actually wrong.
Yes, exactly right. This is where I cheated you a little bit. What does it mean for a Turing machine to fail to solve this problem? What does it mean for a Turing machine to fail to solve a problem? It can either not halt on all inputs, and that's what I told you happens, or, a Turing machine could fail to solve a problem by outputting a wrong answer. Maybe it halts on all inputs, but sometimes it gets the wrong answer. And what would it mean if a Turing machine, what would it mean if this algorithm gave the wrong answer? It'd be a little weird. It would mean that in this ZFC plus first order logic deductive calculus, you might be able to prove something like m of x eventually halts, even though it loops. Or you might be able to prove that m of x eventually loops, even though it actually halts. And what would that mean? Yeah?
There's some contradiction within the axiom.
Yeah, it would basically mean you've got a really bad set of axioms because from them you can deduce false things. Which is also something that's perfectly possible. You can imagine maybe screwing up your axioms or something and making a mistake in writing down those 9 axioms of ZFC such that they're not really modeling the real world of sets and mathematics. They have a bug in them. And that's called being unsound. It might prove some statements that are actually false. Which again, at first, naively, it's kind of possible, but people had, a really long experience with ZFC, and all the axioms seem pretty true, and the deduction rule seems pretty true. So, it's never proved anything false before. So people really don't believe this. And still, actually, after 100 years, people don't believe that ZFC is unsound. We really think that, it's only proving true statements. We've never found, it proving something false. And if it did, that would be extremely surprising, and we would have to cancel the course or something. But it's theoretically a possibility. We want to admit it as a possibility. So this is actually sort of the real statement that we've proved. ZFC, together with this deductive calculus, cannot be both complete and sound. These are technical terms. Complete means that for every sentence S, there's a proof of either S or not S. And remember, it was incomplete in our proof because there's a sentence, m of x halts, that would be S, where you couldn't prove m of x halts, or you couldn't prove negation of m of x halts, which is m of x loops. Or it cannot be sound. Sound means for every statement S, if you can prove it, then it's actually true. So it doesn't prove any false things. And generally, we strongly believe that ZFC and deductive calculus are sound, so it pretty much means that ZFC and the deductive calculus are incomplete. There's some true statements that cannot be proven. Actually, any questions so far? It's getting into slightly funny territory now. It's always weird when you're using math to reason about math, but you should just always have in your head that math is just good old math, and logic, the stuff we're doing is some formal set of rules about manipulating strings. So that's what it is. Okay, let me make a little side question. What did this proof really use about ZFC? Somehow the deduction was about these specific 9 axioms ZFC of set theory. But did we really use the definitions of those axioms very heavily? The answer is not really. we used the fact that you could use the language of ZFC and set theory to define Turing machines, and that you could, it was sort of, we were able to encode mathematical expressions like this Turing machine, it halts on this input, using the terminology of ZFC and set theory. So that's really all we used about it. Oh, we used one other property too, which is that its axioms and its axiom families are computable. We use that when the algorithm is checking whether a long string represents a valid deduction of a sentence. Part of that checking is checking whether, when the proof says like this is an axiom or this is an initial object, the Turing machine has to check that it really is an axiom. Okay, but ZFC has this property that you can tell if a statement is in the axiom list. So to summarize, Gödel's first incompleteness theorem is that any mathematical proof system, ZFC or whatever, that's somehow sufficiently expressive enough to define Turing machines and has computable axioms cannot be both complete and sound. And usually, you only talk about kind of sensible axiom systems that are computable, and usually you only talk about axiom systems that you believe to be sound, because otherwise it's kind of dumb. So basically, the conclusion is that it cannot be complete. It cannot prove all the true things. As a little side remark, it turns out that even Peano arithmetic, remember these like 9 or whatever, 11 axioms about 7 axioms about integers? It turns out if you work hard enough, you can define Turing machines using just integers. It's very annoying, like, even to define like an ordered pair of integers, you use some like crazy scheme where like if you want to define the ordered pair x, y, you encode it by the number 2 to the x times 3 to the y. And there's all sorts of like very painful tricks for encoding like lists and tuples and Turing machines into integers. And like this is something that Gödel did in his original paper because he really wanted to do this for Peano arithmetic. But it's like super annoying. Like 95 or like 98% of the work is like this hacky translation of like how to define ordered tuples and stuff as numbers, which is like programming in assembly language. And like the 2% was like the interesting part that we just did. So I'm going to skip that, but I'll tell you that you can do it. So it implies that there are true statements about natural numbers which you cannot prove using deduced from the Peano arithmetic axioms. Okay, now I call this a smart-aleck's attempt to get around the first incompleteness theorem. Actually, it's not such a silly attempt. It's a natural thing to think about. You might say, okay, fine. So let's assume that ZFC, our favorite deductive set of axioms for math, is sound. So Gödel's theorem tells us there's some true statement which cannot be proved in ZFC. All right, cool. Let's just make it an axiom. Now it can easily be proved because it's an axiom. I mean, you can prove it in one line. So great. So why does this not really fix anything? I mean, why does this not suddenly solve all the world's problems? Like, now can we prove all true statements? Yeah? It's not going to make the system unsound because S is, a true statement. So it's okay to add like a true statement to your axioms. That will not make them unsound. And it could be that like not only is there one true statement that cannot be proved from ZFC, but there could be very many, like infinitely many true statements. But maybe once you add this one true statement S, now suddenly you can prove all the true statements. Yeah?
ZFC plus S is still expressive enough to express the Turing machine, so therefore it's much more convenient.
Yeah, exactly. That's fine. You can define a new set of axioms, ZFC together with S, in the same deductive calculus. But then you can just apply Turing's theorem to it again. Or sorry, Gödel's theorem to it again. ZFC together with S still can talk about Turing machines and so forth. It still has computable axioms. So by Gödel's theorem, there's some other true statement S prime that you cannot prove. So you could say, great, I'll add in S prime as another axiom, but this doesn't help. I mean, ZFC together with the axiom S, together with the axiom S prime, whatever they are, you can apply Gödel's theorem to it and get a new true statement, S double prime, which is true, but cannot be proved. So you keep maybe, you find your axioms weren't strong enough to prove all the true things. You're like, oh, let's just add some more true things to the axioms. But, you can always apply Gödel's theorem. So you can never catch up. There will always be more true statements that you cannot prove. Does that make sense? Now, you can actually take this one step further, and you could say, I'm just going to add in all true statements as axioms to my deductive system. And that's actually, you can do that if you want. It's perfectly fine. But there's a non-satisfactory aspect to this. Can somebody say what's not really satisfactory about this? Yes?
Is it not computable anymore?
Yeah, it's not really computable anymore. I mean, it's technically a deductive system, but your deductive system is just step one. As an initial object, you can have any true statement. Well, fine, but you've defeated the purpose of having a deductive system at that point, right? Because the whole point is you can no longer check whether you can no longer easily check whether a given statement is an axiom, right? So now the set of axioms is not computable, so it's kind of pointless. I mean, it's no longer helping you in this proof formalization process. Okay. Now, there's another common reaction that you may have to Gödel's first incompleteness theorem, which is about this definition of sound, which is that for every statement S, if S is provable, then S is true. Many people, including me, every time I'm giving this lecture and remembering these slides, I'm like, wait a minute, what does it mean to be true if you cannot prove it? How can you say a sentence is true if you cannot prove it? What does that even mean? And the resolution of this, well, there's a sort of a two-part resolution. First step is to don't get confused. I mean, if I ask you yesterday, hey, is this statement true? 1 is the only number appearing in Pascal's triangle more than 10 times. That's just some math question. Is it true that the only number in Pascal's triangle appearing at least 10 times is 1? If I ask you, hey, is that true yesterday? You would not be like, whoa, man, what is true? You would just say, I don't know. I mean, it could be true. It could be false. I'll see if I can prove it. I mean, you wouldn't I don't think you would doubt whether or not there was an answer, is it true or not? You would probably accept that it's either true or false, right, without worrying about it. And that's what you should continue to do. This statement is either true or false. Maybe we don't know which. And maybe you cannot find the solution with a proof using ZFC's axioms, but it could still be true or false. Okay, so good old regular mathematics does not become invalid just because you happen to be studying logic today. I mean, we're just studying whether you can make a mechanical string manipulation system that can generate this as a valid deduction. But whether or not that's possible doesn't change whether or not this statement is true or not. Is it okay? I mean, this is probably the most confusing part of everything. Okay. Now, Gödel back in the 30s also anticipated this difficulty, and Gödel was if I just say this to the mathematical world, hey world, don't get confused, they're going to be kind of mad. And it's a tricky concept, I mean, for sure. So what he did was, he's just so nobody gets confused, I'm going to prove a stronger version of my theorem that doesn't even use the word truth. So if you're confused about what is truth, it doesn't matter because my theorem does not even mention truth. Okay, so this is the full version of his theorem, the strong version. Actually, Gödel couldn't quite prove it. He had some technical annoyance that he couldn't quite prove, which was fixed by this guy Barclay-Rosser. And this is the real Gödel's first incompleteness theorem. So as any mathematical proof system, like ZFC or whatever, which is sufficiently expressive and has computable axioms, okay, this is the real conclusion, cannot be both complete and consistent. Remember, it used to say complete and sound. Now it says complete and consistent. So remember, complete means every statement, you can either prove it or disprove it. I mean, every statement can be resolved as provable or not provable. Consistent means there's no statement where you can prove S and its negation. Okay, that's consistent. For every S, you can't prove both S and not S. Okay, so actually complete and consistent kind of says for every statement you can prove exactly one of S and not S. Sort of you can exactly resolve the provability of every statement. And what's the relationship between consistency and soundness? Can somebody say? This also you have to think about a bit, but the relationship is that if you have a system that's sound, then it's also consistent, because sound means it only proves true things, and you can't have both S and not S being true. So if you're sound, then you're definitely consistent. It's not the converse. I mean, you can have a consistent system that's not sound. Like you can have some sort of deductive system about proofs that has the consistency property. It never proves both S and its negation, but it might have like no connection to reality and truth. But the converse is the case. A sound system is automatically consistent. So this is actually better than the original version that said you can't have a system that's both complete and sound. Not only can it not be sound, it can't even be consistent. Okay, so mentally, mainly you think of the conclusion is that it cannot be complete and sound. If it's proving only true things, then it cannot prove everything. But this is a better version, because consistent is a weaker condition. You can't even get it. And the good thing from Gödel's point of view is that this doesn't mention truth anywhere. It's just, this is all syntactic. It's just about what kinds of strings it can generate, this proof system. Okay, so this slide is also a little bit complicated. Any question? No? Okay, well, I'm going to prove this stronger version to you. I proved the weaker version quite easily using Turing's theorem, where it was about complete and sound. And now I'm going to prove the stronger version to you. And there's going to be a twist at the end, like a plot twist. So keep your eyes open. Okay. For simplicity, I mean, this statement is about all sufficiently expressive systems, whatever. But let's just say ZFC, the official sort of formal system for deducing regular mathematics. So the previous proof had the following outline. We assumed that ZFC is sound, that you would never have proofs of false statements. And then we invented this Turing machine that is very closely related to the halting problem. And we concluded that it was incomplete, that there had to be some statement, there had to be some Turing machine and some x, such that it either couldn't prove m of x halts and it couldn't prove m of x loops. So it was incomplete. And that was the previous proof. Now we're going to give a stronger proof of this, a proof of the stronger statement, where this is a weaker assumption. We're only going to assume that ZFC is consistent, that it never proves both a statement and its opposite. Then we'll reason about a certain Turing machine, and we'll deduce that ZFC is incomplete. Okay, so that'll show that it cannot be that ZFC is both consistent and complete. Okay? It's a pretty simple proof. We'll need one small lemma. So I will do this lemma now. We've been talking a lot about whether or not you have a true statement, whether or not you can actually prove it using your deductive system in ZFC. And maybe sometimes there's a true statement that you cannot prove. But there's some cases where statements are so simple that if they're true, they definitely have a proof. Let me give you an example. This is a statement. There are 25 primes less than 100. Does anybody know if that's true or not? Oh, it is true. Yeah, who said that? It's pretty good. Well, whether or not you know it's true, it is true, as it happens. You know that you're going to be able to prove it. I mean, forget ZFC for a second. Suppose this was on your homework. Prove this. I wouldn't have put it on unless it was true. And you could be very happy because you kind of know there's got to be a proof. You can sort of automatically tell there's going to be a proof. Maybe you could do something clever, but in the worst case, you can just literally write down all numbers between 1 and 100. For each one, you could literally write out all possible potential factors. Literally write out a proof that they don't divide into it. there's going to be like a brute force proof, okay? Some sort of brute force, like brain dead enumeration proof, where you don't have to use your head. You can just sort of automatically be sure there's a proof. Like, in contrast to this is, remember I mentioned this other random statement. 1 is the only number that appears in Pascal's triangle at most 10 times. So let's say that that's true, and I ask you to prove it. It's like a homework problem, right? It's like not clear what you're going to do. It's not clear how you would prove it. You can't sort of like automatically do a brute force proof. Maybe it's not even clear whether there is a proof, right? But there are some statements like, you know, the number 3 appears in Pascal's triangle twice, that if it's true, it's definitely provable. You just like write it down, and you're like, there it is. So the particular brain dead lemma that we're going to use is that the following is true. If you have some particular Turing machine, and it has a particular t-step execution trace, then there is a proof of the fact that it has that execution trace in ZFC. Okay, it's just saying that like ZFC has all the language it needs to like, you know, follow the execution of a Turing machine for t steps. So why is this true? Well, you can just always write like a brute force brain dead proof with like the configurations where you're like, well, the first line of my proof is like, by definition, this is the starting configuration of the Turing machine. The second line of my proof is, by definition, after 1 step, you're in this configuration. By definition, after 2 steps, you're in this configuration. And you could just write out like a proof with like t+1 lines in it, and that would be the proof. Okay, so I know this is a bit of a weird concept, but this is what we want to show. Or this is what I claim is true. And in particular, as a little corollary of it, you see that if you have a particular Turing machine M and a particular string x, and it's true that M of x halts, there will always be a proof of the statement M of x halts. Because if M of x halts, it halts in some finite number of steps t. And then, in the worst case, you could just write down like a proof with like t lines in it that says, on M running on x, first it looks like this, then it looks like this, then it looks like this, and then it enters an accepting state. Yeah, I think you even had to do this in like one homework, like literally list out all the configurations and show that it ended in a halting state, or in an accepting state, or whatever, that it halted. Okay, any questions about this brain dead lemma? It's kind of simple in a way. Okay, we now have all the pieces together. We're going to finally finish proving the full, strong version of Gödel's first incompleteness theorem, the truth-free version that says CFC, or any formal system, cannot be both consistent and complete. So in other words, if you assume it's consistent, that it never proves both a statement and its negation, then it can't be complete. There has to be some statements that it can't prove and can't disprove. Okay, are we ready? Questions? Okay, well, I told you the first line of the proof of Gödel's first incompleteness theorem. It's assume ZFC is consistent. Okay, and the last sentence is going to deduce that ZFC is incomplete. Okay, so there's the first sentence. I think it's going to won't quite fit on one slide. Okay, so as always in these proofs, like you do it by inventing like a weird Turing machine and real reasoning about it. It's going to be very similar to the one we saw before. It's practically actually the same, actually. So let D be the Turing machine, which takes as what input a piece of code, or a Turing machine, M. And what does it do? It goes through all strings, and it checks whether it's a valid proof of the statement M halts when run on itself. And if it finds such a proof, it does the opposite. It enters, the Turing machine D has like some state that just always goes right, like write a blank and go right, and come back to the same state. So it enters this like trivial go right forever state, which means it gets it into an infinite loop. On the other hand, if it finds that P is a proof of M loops, then it halts. Okay? This is a Turing machine. This is a perfectly normal Turing machine. Like, okay, you could probably make it with like, I don't know how many states, but you could write like some simple Python code that did exactly this. There's nothing weird about this Turing machine, per se. But now we ask the question, what can you prove using ZFC and deductive calculus about what happens when you run D on input D? It's always the game. Now here's where we're going to use this assumption. We made this assumption. We use it right now. By consistency, it can prove at most one of these two statements. These statements are the negation of each other. D of D halts. The negation of that is D of D loops. So consistency says it cannot prove both of them. It proves at most one of them. And we're eventually going to show, in a couple more paragraphs, that it actually proves none of them. And that means it's incomplete, right? That means you have a sentence where you cannot prove this and you cannot prove its negation. Okay, so far we know that it proves at most one of them. I'm going to do a little reasoning and actually show that it doesn't prove either of them. Okay, and that will be the end of the proof. So let's see. Let's try to do some cases. Maybe there's a proof in ZFC that D of D loops. I'll show you how you get a contradiction then. Here it is, in fact. So suppose there exists a proof that D of D loops. So now think about what happens when you run D on input D. When you run D on input D, it starts going through this loop, checking to see if there's a proof of D of D halts or D of D loops. Now, if CFC proves D of D loops, by consistency, it doesn't prove D of D halts. It can prove at most one. So that means when D is running on itself, it'll never do this step. Because there is no ZFC proof that D of D halts. And on the other hand, it definitely will hit this line eventually, because we're assuming here, for contradiction, that there is a proof of D of D loops. So it'll find this proof, and then it'll halt. So D of D would actually halt. And then we know, by the brain-dead lemma, if you have a Turing machine and a string, such that the Turing machine running on its string halts, there's always a proof of that. You can always, if a Turing machine really halts on a certain input, you can always have a proof of that in ZFC. So if it really does halt, then there's a proof that it halts by the brain-dead lemma, and then we get a contradiction, because ZFC apparently now proves that D of D loops and that D of D halts. And that contradicts consistency. Okay. Any question? Kind of at this, yeah.
So when we say that we can prove D of D loops, we're never saying that D of D actually loops.
Yeah, here we're assuming that we're doing a little proof by contradiction here. We're assuming that ZFC can prove the statement D of D loops. And from that, we're deducing that in reality, if that's true, then D of D will actually halt. And then we're using the brain-dead lemma to kind of upgrade that statement from this statement is true to the stronger version, there is a proof of this statement. And it's true, I mean, we can do that because this is a very simple statement. If D of D halts, there's definitely a proof that D of D halts. So we can kind of move from like truth to like the more syntactic statement, there's a proof of this fact. Okay, so by its consistency, at most one of these two statements can be proved. And we just showed that this one cannot be proved. And now I'm going to do the same thing. I'll prove by contradiction that this one also can't be proved. D of D halts. It's very similar, just a tiny bit trickier. It fits like this. So let's assume for the sake of contradiction that there is a proof of D of D halts. Well, again, by consistency, if there's a proof that D of D halts, there's no proof of D of D loops, the negation. So when this D starts running on D, it'll never do this line, because there is no proof of D of D loops. And it will definitely eventually do this line, because we're assuming that there is a proof of D of D halts. And what happens when it hits this line, it enters into this go right forever state. And so that means, in reality, in truth, D of D eventually hits the go right forever state. So it's not the case that D of D halts. It actually loops, but it kind of loops for a trivial reason. It runs for a finite amount of time, t steps, and then gets into this go right forever state, which is like an obvious infinite loop. So I'm using the brain-dead lemma here in a slightly more subtle way. I'm saying, not only does D of D eventually loop, there's definitely a proof of that, because the proof will just look like, okay, here are the configurations for a while, and then the last configuration I'll show you is it entering into the go right forever states. And then, I'll write like another sentence saying like, now it will loop forever because it's in this go right forever state. Okay, and so therefore, not only does D of D loop in this case, there's actually got to be a proof that D of D loops. And then that contradicts consistency again. Because we have a proof that it halts and that it loops. OK. Any questions? So we're actually done. We did it. We just show that Z of C, first we used consistency to show that it could prove at most one of these statements. And then we did a little case on it and showed that it doesn't prove this one, or it doesn't prove, and it doesn't prove this one. So therefore, we've done it. We found a statement, let's say D of D loops, that Z of C can't prove and it can't disprove. And it's not even a weird statement. I mean, D is like a totally explicit Turing machine. There it is. And Z of C cannot prove or disprove that D running on itself halts. So that's it. Now, that's the end of Gödel's first incompleteness theorem. Now let me ask you a question. This is all like some arguments in math about whether a certain Turing machine halted and whether there are proofs in this deductive system of something or other. But anyway, D is like a real Turing machine. It's right there. Between you and me, in truth, what actually happens when you run D on D? Does it actually halt or does it actually loop? It loops. That's right. Why does it loop?
Because you just showed that you can't prove either of those.
Yeah.
So it just will never stop.
Yeah. So in actuality, there is no proof of this or this. So none of these lines, when you actually run D on D, it'll never find the proof of this. It'll never find the proof of this. So it'll just keep going forever. So the true statement is that D of D actually loops. But there's no proof of that fact. Now here's the plot twist, OK? Now wait a minute. We, like us together, on the last 3 slides, just showed that D of D loops. I mean, we did. We showed it. But I have also told you all along, and I wasn't lying to you all along, that whenever you can prove something using good old regular mathematics, if you work hard enough, you can translate it into a proof of Z of C and the deductive calculus. They did it for the 4-color theorem and the Kepler conjecture. And this is not even that complicated. Whenever I tell you a regular math proof, you can put it into the Z of C language. But wait a minute, we just proved that D of D loops. And also somehow that there is no proof that D of D loops. So, if we just formalize these last 3 slides in Z of C, we actually get a proof that D of D loops, which is like a contradiction. So perhaps we just found a contradiction in all of mathematics. And then we can really cancel the class. Well, did we find a contradiction in mathematics? The answer is no, because I cheated you a little bit again. I put a little something past you that you might not have noticed. We didn't find a contradiction in mathematics. And the problem is with this last statement. If we formalize these last 3 slides, we didn't actually really show that D of D loops. Because, you see, we forgot about this line here. Well, we really show that if we formalize these last 3 slides, what we get that if you assume Z of C is consistent, then D of D loops. If you assume Z of C is consistent, then we really deduced that Z of C can't prove D of D loops and it can't prove D of D halts. So therefore, this program will run forever. OK? And I managed to cheat you because you rarely think about the case that Z of C is inconsistent. We kind of believe that Z of C is consistent. It doesn't, prove a statement and its negation. So we kind of forgot about this a little. And so we just assume that this is always true. And therefore, there is no proof that D of D halts or D of D loops. And so this will run forever. But really, in order to make that conclusion correct, you have to remember that Z of C is consistent. I mean, it could be maybe Z of C is inconsistent. And therefore, even though D of D halts or loops, maybe there's a mistake in the code here, because you actually find a proof of a false statement. So what we really proved is this. If Z of C is consistent, then D of D loops. And we proved that using good old regular mathematics. Yeah?
But doesn't that still imply if Z of C consistent, then Z of C not consistent?
Close. This is exactly what I'm going to say now. What's really true is that using regular mathematics, we proved that if ZFC is consistent, then this program, when run on itself, loops. Now, I'm going to make a further observation. Let's suppose that ZFC is really actually consistent, which is something we always do. Then, in that case, we show that d of d loops. We can show that d of d loops. I mean, that's like the cheating proof I just gave you. If ZFC really is consistent, then we really can show that d of d loops. We just saw that proof. And we also know that there's a proof that if ZFC is consistent, then d of d loops. So in order to avoid like a contradiction in all mathematics, the only thing that's left that's possible is that there's no ZFC proof of ZFC consistent. Okay, like forget for a second like what this like ZFC consistent and d of d loops. Just imagine this statement is statement A, and this statement is statement B. We know that assuming ZFC is consistent, you can prove statement B, and you can prove A implies B. So, wait a minute. I got confused here. What do I want to say? They always trap you. Right, let's go back. Right, the conclusion was that assuming ZFC is consistent, you can't prove d of d loops or d of d halts. And under that assumption, we showed that d of d actually loops. And if you formalize these slides, you get that if ZFC is consistent, then d of d actually loops. So the only way you can avoid this contradiction is if ZFC cannot prove this statement A, that ZFC is consistent. Because then you would really get, if it could, then you would really get a contradiction. It could prove that ZFC is consistent. It can prove this statement. So it can prove like this. It can prove the implication. So it could also prove that the conclusion, that d of d loops. But this is what we showed is not possible. So the extra plot twist is that you get like an explicit, interesting statement that ZFC cannot prove. And this is Gödel's second incompleteness theorem, also proved independently by von Neumann, which is that if you assume ZFC is consistent, then not only is it incomplete, here's a particularly interesting true statement that it cannot prove. ZFC is consistent. So much like with the halting problem, we originally showed that there are some uncomputable languages, and then Turing came along and said, actually, not only is there an uncomputable language, there's a particularly interesting one, the halting problem. Similarly, Gödel's first incompleteness theorem tells you, if you just write down ZFC, not only is there some statement that you cannot prove or disprove, here's a particularly interesting statement that you cannot prove or disprove. ZFC is consistent. So like, no matter what formal system you write down, it cannot prove its own consistency. And this is supposed to be like the mind-blowing aspect of Gödel's second incompleteness theorem. In fact, actually, there's some other theorems that have this property. So much later, Cohen proved this statement about something called the continuum hypothesis that Anil mentioned once. Anil asked you whether we know that the cardinality of the reals is bigger than the cardinality of the natural numbers, and asked whether there's some set that was in between. And it turns out that this is another example of a statement that cannot be proved or disproved using the regular rules of mathematics, ZFC. OK, so that's it. Have a good spring break.